Hello students, welcome to EPG Pathshala. I am Snelata Pawar from the School of Life Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to talk on the module Introduction to Carbohydrates from the paper Biomolecules and their interactions. So the objectives of this particular module is to introduce you all to the importance of carbohydrates, especially monosaccharides, vis-a-vis the functions of carbohydrates, followed by examples of monosaccharides and some very important polysaccharides. We will then have a look at how monosaccharides are used as building blocks for building up long-chain carbohydrates. We will see how these monosaccharides are put in together and long-chain polysaccharides are synthesized from the monosaccharides. And then we will talk about reactions that are specific to carbohydrates and are used to quantitate carbohydrates or sugar in a given solution. So let's first start with the basic definition of carbohydrates. So what are carbohydrates? Carbohydrates are considered the most abundant biomolecules that exist on Earth. Carbohydrates consist of monosaccharide, which is basically the minimal unit building block for the construction of di, tri, tetra, oligo, and polysaccharides. So monosaccharide molecules, they consist of three atoms, namely carbon, hydrogen, and oxygen. And as you can see here, a carbohydrate can be depicted by the empirical formula that is shown here, where you see that there is one molecule of carbon, two atoms of hydrogen, and one atom of oxygen. And these carbohydrates are basically, as the name suggests, are also referred to as hydrates of carbon. So now, for example, if you consider a hexose, say glucose molecule, so how many carbon atoms does the hexose or glucose will have? It will have 6 carbon atoms. So for every 6 carbon atoms, there would be 12 hydrogen atoms and 6 oxygen atoms. The N that you see in this empirical formula should be greater than or equal to 3. So all carbohydrates are basically polymers of sugars or saccharides. Or in other words, you can say that monosaccharides are used as the building blocks to build up long-chain carbohydrates, which are also called as oligosaccharides or polysaccharides. And as we continue through this module, we will see how these long-chain polysaccharides are built from the monosaccharides. So why are carbohydrates important for our body? There are different biochemical roles that carbohydrates serve in our body. The first biochemical role of carbohydrates is that they are very good energy sources, such as glucose, sucrose, fructose. They are all simple sugars, and all of them end in the suffix -ose, O-S-E, as you note here. Okay? They are all able to store energy as covalent bonds in the carbon-carbon single bond or the carbon double bond O, which is also called as the carbonyl group. So because the energy is stored in these compounds, in these covalent bonds, these molecules are good energy sources for the body. The second important biochemical role of carbohydrates is that they serve as energy storage forms in our body. So for example, starch is the storage form of glucose in plants, while glycogen is the storage form of glucose in animals. And glycogen is found predominantly in the liver and in the muscle of the animals. The third important biochemical role of carbohydrates is that they can be used as structural material. They are great carbon skeletons and hence can build structures such as cellulose, which is a very important component of the plant cell wall, and chitin, which is an important component of the fungal cell wall. Carbohydrates, as I've already mentioned, are polymers of sugars or saccharides. So the basic definition of a polymer is that a polymer means many somethings or many mers. Okay, so basically carbohydrates are repeating units of monomeric sugars, say for example glucose. So you see different ways in which a glucose molecule is represented here. It can be represented in different ways, in a cyclic form, in a linear form, and as we move on, we will see what these representations actually mean. Now, if you look at the structure of glucose, the question that comes to your mind would be, is this molecule soluble in water? And if it is soluble in water, then what is the reason why it is soluble in water? Now, one reason why these compounds will be soluble in water is because of the presence of the important functional group that shows over and over again in this molecule, which is basically the hydroxyl group here. And since hydroxyl groups are polar, so these compounds are soluble in water. So let us just have a look at now how two monomers are brought together and linked through a glycosidic link. And basically it's this glycosidic linkage that connects one sugar molecule to the other, to the third, to the fourth, so on and so forth, and is basically connecting all the sugar molecules and is the basis for the synthesis of oligosaccharides or polysaccharides. So what happens during this kind of the formation of glycosidic linkages, you consider these two monomers that are drawn here. So if I take out the hydroxyl group from one sugar and hydrogen from the other, what do I end up with? I end up with a water molecule that has come out from these two sugar molecules. And then what I can do is, if I connect these two monomers through the oxygen atom that is left on one of the monomers, then what I eventually build is a link that is called the glycosidic link, as you can see here, which is marked by a red arrow. This is the glycosidic linkage. So since we pulled a water molecule to build a bond, or in other words, since we dehydrated two molecules to synthesize a disaccharide, hence this process is referred to as the dehydration synthesis, or it is also referred to as sometimes as a condensation reaction. The monosaccharides can be divided into aldoses and ketoses. What is the difference between an aldose and a ketose? The aldoses carry an aldehyde functional group at the first carbon. If you look at the structures depicted on the right hand side, you notice that there is a molecule called glyceraldehyde, then there is glucose, and in all these molecules at carbon 1, the functional group is an aldehyde group. So these sugars, for example, glyceraldehyde and glucose, are considered aldoses, while the ketoses like fructose, as shown on the right hand side, will carry a keto group usually at the second carbon. Glyceraldehyde is the simplest 3-carbon triose. It is a 3-carbon, it's called a triose because it contains 3 carbon, and it's a aldose because it contains a aldehyde group as the functional group. So the chain of carbohydrate can be constructed by substitution of a terminal carbon-hydrogen bond with increasing number of CH2OH units. So looking at the basic definition of aldose and ketose, we can say that glucose is an aldohexose, which means that glucose has 6 carbon atoms and it has aldehyde as a functional group, while fructose is a ketohexose, which means that fructose also has 6 carbons just like glucose, but instead of an aldehyde group, it has a keto group at C2 position. So one important characteristic of monosaccharides is that they can exist as isomers. All monosaccharides except for dihydroxyacetone phosphate consist of asymmetric carbon centers, which are also called as chiral carbon, because of which monosaccharides are optically active. Isomers, as we know, the basic definition of isomers is that two compounds will have the same molecular formula, which means that they would have exactly the same number of atoms and the same type of atoms. But in the case of monosaccharides, these isomers will differ from each other in terms of the arrangement of these atoms in space. So there are two kinds of isomers that exist in monosaccharides, enantiomers and diastereoisomers. Enantiomers are those isomers that are basically non-superimposable mirror images of each other, and we will see what these look like. And diastereoisomers are those isomers that are not mirror images of each other. Epimers is a specific type of diastereoisomer, and these epimers basically they differ in stereochemistry only at a single chiral carbon atom. So like I mentioned, monosaccharides exhibit isomerism because of the presence of asymmetric centers within these molecules. So all monosaccharides, with a few exceptions like dihydroxyacetone phosphate, contain one or more asymmetric carbon atom, which is also called as the chiral carbon atom, and hence exist in optically active isomeric forms, which are called as enantiomers. So you can see that there are two different sugar molecules, structures of two different sugar molecules that are depicted here, and there are two designations of each of the sugar molecule that we have mentioned here. So you see that there's a D-glyceraldehyde, there's a L-glyceraldehyde. Similarly, there's a D-erythrose and a L-erythrose. So what do we mean by these D and L designations? So the simplest triose or an aldose sugar is glyceraldehyde, as I've already mentioned before. It's a triose because it has 3 carbon atoms, and you can see that carbon at position 2 is basically the asymmetric carbon atom because the 4 functional groups that are attached to this carbon atom are different. And so this molecule becomes asymmetric, and since it is asymmetric, it is an optically active compound. So all D sugars have the same absolute configuration as the asymmetric center that is farthest from their carbonyl group, as does D-glyceraldehyde. So in D-glyceraldehyde, at the asymmetric carbon atom, which is C2, you see that the hydroxyl group is placed on the right side. In the L-glyceraldehyde, the same hydroxyl group at C2 is positioned on the left side. Similarly, now if you have to designate an erythrose molecule with a D or an L, as you see here, the molecule would be designated as D if the hydroxyl group that is farthest from the functional aldehyde group is placed on the right side, similar to the glyceraldehyde molecule. So whenever the hydroxyl group is placed on the right side, the molecule is designated as D, and if it is placed on the left side at the asymmetric carbon center, which is farthest from the carbonyl group, then it is designated as L. And so for D-erythrose, you see that the carbon at position 3 is the farthest carbon, which is asymmetric, and the hydroxyl group here is placed on the right, just like D-glyceraldehyde, so it is called as D-erythrose, while the hydroxyl group in L-erythrose is placed on the left-hand side, just like L-glyceraldehyde at C3, and so this erythrose molecule is designated as L-erythrose. So glyceraldehyde has a single chiral center. As you can see that there's one asymmetric carbon center which is marked with an asterisk here. And so it can exist in 2 optically active isomeric forms. So the number of optically active isomeric forms that a sugar molecule can form can be calculated by a formula which is basically 2 to n, where n is the number of asymmetric carbon centers in a molecule. Since glyceraldehyde has 1 asymmetric carbon atom, So if you apply this formula to glyceraldehyde, the number of possible stereoisomers that glyceraldehyde can have is 2 raised to the power 1, which means 2 possible stereoisomers, as we see in this figure here. So basically, enantiomers are those compounds that are mirror images of each other. So they are isomers, but they are mirror images of each other, and these mirror images are non-superimposable. So enantiomers are basically optically active compounds that are mirror images of each other, which are non-superimposable. So I have been using this term optically active isomers, and we have now defined enantiomers as those compounds that are optically active and are mirror images of each other. So what does this optical activity basically mean? And how is this optical activity measured? So the physical properties of the D and L enantiomers are generally the same, but these enantiomers, they differ in the way they rotate the polarized light. And we will see what this rotation of polarized light actually means. So how can you measure the optical activity of a compound? There is an instrument called a polarimeter, which is used to measure the optical activity of the compound. So as you can see here, normal monochromatic light contains light that possesses oscillations of the electrical field in all possible planes perpendicular to the direction of propagation. Now, if this light that is propagating in all directions is passed through a polarizer, which can be a Nicol prism or a Polaroid film, only light oscillating in one plane will leave the polarizer. As you can see that the light that was transmitting in all directions is now only moving in one direction. The linear polarized light that you see here, which comes out after it has passed through the polarizer, is actually a result of a superposition of two components that counter-rotate. Okay, so which will then propagate with different velocities in an optically active medium. So now this plain polarized light, if it is allowed to pass through a tube that contains a solution of an enantiomer, what will happen? If one component interacts stronger than the other with a chiral molecule of this enantiomer, this component will slow down and will arrive later at the observer. As a result, the plane of the light appears to be rotated to the observer. In order to achieve maximum brightness, the observer will now need to rotate the axis of the analyzer either clockwise or anti-clockwise, depending on the type of the compound that we have placed in the tube. So a monosaccharide for which the axis of the analyzer is rotated in the clockwise direction is designated as plus and is called dextrorotatory. On the contrary, if the axis of the analyzer is rotated in the anti-clockwise direction, the monosaccharide is designated as minus and is called levorotatory. So the D and the L designations that we saw previously do not represent the optical activity actually. The optical activity is represented as either plus or minus, or it is designated as a small d and a small l. So let us just have a look at the different properties of enantiomers. So as I've described previously, the enantiomer that will rotate polarized light to the left is referred to as levorotatory and is designated with the minus sign. The enantiomer that rotates to the right is dextrorotatory and is designated with the plus sign. So basically the D and the L designations that you have seen before do not represent dextrorotatory and levorotatory. The property of rotating the plane of polarized light is called optical activity, and the molecules with this property are said to be optically active. Measurements of optical activity are useful for differentiating between enantiomers, and as we have seen previously, that we use an instrument called polarimeter to measure the optical activity of these optical active compounds. So we've already seen one kind of stereoisomerism that exists in monosaccharides, which is enantiomerism. Diastereoisomers is another kind of isomerism that is exhibited by the sugar molecules. So how do you define diastereoisomers? When two sugars have the same exact molecular formula, the same number and type of atoms, but they differ in the arrangement of their atoms in space and are not mirror images of each other, then these isomers are referred to as diastereoisomers. So you look at the two compounds that we have, the two sugar molecules that we have shown here. One is D-erythrose, the other is D-threose. So if you draw a line in between these two sugar molecules, you will notice that erythrose and threose, both they're not mirror images of each other. So basically anything that is not an enantiomer is a diastereoisomers. So what you have to note here is that both the compounds, erythrose and threose, they have the same number of carbon atoms. They have the same kind of functional group. So both of them are basically aldoses because they have an aldehyde group. The only reason, and both of them exist in the D form because the hydroxyl group that is positioned at C3 is placed on the right hand side, just like D-glyceraldehyde. The only position where these two compounds differ is at C2, where in one case the hydroxyl group is present on the right side. In the case of threose, it is present on the left side. So these compounds, they are diastereoisomers because they are not mirror images of each other, although they have the same identical molecular formula, but the arrangement of atoms differs between these two molecules. So unlike enantiomers, the difference between enantiomer and diastereoisomers is that while enantiomers are non-superimposable mirror images of each other, the diastereoisomers are not mirror images of each other. So a specific type of diastereoisomers is called as epimers, and two molecules are said to be epimers if they differ in their stereochemistry only at a single carbon atom. So you see here glucose, mannose and galactose, which are basically epimers of each other. And what these molecules, how are they different from each other? These molecules are epimers because they differ in their stereochemistry only at a single carbon atom. So if you look at the structure closely, you will see that mannose is an epimer of glucose at C2 as marked in red, while galactose is an epimer of glucose at C4. It doesn't matter which carbon atom, around which carbon atom the stereochemistry differs, as long as that carbon atom is a chiral carbon atom in the molecule. So D sugars are more abundant in nature, and very few sugars will exist naturally in the L forms. L-arabinose and L-isomers of some sugar derivatives are common components of glycoconjugates. So while most of the sugars that occur naturally occur in the D form, the L forms are rare, and you will usually find them only as some common components in glycoconjugates. Monosaccharides vary in configuration and conformation. There is a difference between these two terms. So two conformations of a molecule are interconvertible without the breakage of covalent bonds, whereas if you talk about two configurations can be interconverted only by breaking a covalent bond. We know that in general, the alcohols have a tendency to react with the carbonyl group of aldehyde and ketones, and when that happens, it leads to the generation of hemiacetal in the case of an aldehyde and hemiketal if the alcohol group has reacted with the carbonyl group of a ketone. So, analogous to this situation, if we look at the structure of a monosaccharide, we know that both kinds of these groups exist in a single sugar molecule. So for example, if you look at fructose as shown here or glucose, you know that there are multiple hydroxyl groups that are present within these two monosaccharides, and there is a functional aldehyde group or a functional keto group in fructose and glucose. So the reaction between the hydroxyl and the aldehyde group or hydroxyl and the keto group can take place within the molecule, and this is called an intramolecular rearrangement that takes place in the monosaccharides. So if this kind of an intramolecular rearrangement takes place in glucose or in fructose, it leads to the generation of cyclic structures which are called as cyclic hemiacetals or cyclic hemiketal. So in the case of fructose, if the hydroxyl at C5 reacts with the carbonyl oxygen at C1, it leads to a generation of cyclic fructose, which is called as alpha-D-fructofuranose. In the case of glucose, if the same kind of a cyclization occurs between due to the reaction between the hydroxyl group at C5 and the carbonyl group at C1, then you see that it leads to the generation of glucopyranose. So in the case of fructose, if the hydroxyl group at C5 reacts with the carbonyl group at C2, it leads to the generation of a cyclic structure of fructose, which is called as fructofuranose. Similarly, in glucose, the hydroxyl group at C5, if it reacts with the carbonyl group at C1, it leads to the generation of glucopyranose. These cyclic representations of sugars are referred to as Haworth projections. So upon cyclization, the cyclic sugars can have two anomeric forms. So what basically happens here is that when the hydroxyl group at C5, as shown in green in the figure here, attacks the electrophile at C1, which is shown in purple, it results in the generation of two different cyclic forms which are referred to as alpha and beta forms, and the alpha and beta forms are known as anomers. When the hydroxyl group attacks the carbonyl group at C1, the oxygen atom that is depicted here in purple becomes a hydroxyl group that is shown in the ring forms. So there is basically an alpha form and a beta form that is generated by this intramolecular rearrangement, as the nucleophile at C5 can attack the C1 from either the top side or from the bottom side. So now what is the difference between the alpha and the beta cyclic structures that are generated as a result of this intramolecular rearrangement? So if you look at the alpha D-glucopyranose and the beta D-glucopyranose structure, you will see that the stereochemistry at C1 is different between the alpha and the beta forms, while the stereochemistry at all the other carbon atoms is the same. So the pair of stereoisomers that differ in configuration at the anomeric carbon, which is the C1, are called as anomers, and this anomeric carbon that is referred to here, it then becomes a chiral center. Now, in the anomer, the hydroxyl substituent in the alpha anomer, if you notice, the hydroxyl substituent of the anomeric carbon is on the opposite side of the sugar ring from the CH2OH group at the chiral center, and it is the opposite for the beta form, where you see that the hydroxyl substituent of the anomeric carbon is on the same side of the sugar ring as the CH2OH group at the chiral center. Now, these two anomeric forms, the alpha and the beta glucopyranose, they will differ from each other in their physical as well as their chemical properties, and they will also be differing in terms of their optical rotations. So these anomers in a given, if they're placed in an aqueous solution, the anomers can be interconverted from one form to the other. So these anomers can interconvert in aqueous solution in such a way so that at equilibrium, D-glucose is a mixture of the beta anomer. So there would be about 63.6% of beta anomer in an aqueous solution of D-glucose, and about 36.4% of the alpha anomeric form of D-glucose in an aqueous solution of glucose. So this interconversion of the between the alpha and the beta forms is called as mutarotation. So now the question that will come to your mind is that why should the beta anomer predominate in an aqueous glucose solution as opposed to the alpha anomer? So the answer to the question as to why the beta anomer of glucose predominates in the aqueous solution as opposed to the alpha anomer lies in examining the chair conformation of the glucopyranose structure, of the alpha and beta glucopyranose structures. So let me just also mention here that a sugar with a 6-membered ring is referred to as pyranose, which is why we have been calling the cyclic structure of glucose as glucopyranose, while sugars with 5-membered rings are called furanoses, and therefore we referred to the cyclic structure of fructose as fructofuranose. So the pyranose structures can adopt a chair conformation wherein there can be two kinds of bonds. In the chair conformation, there are equatorial bonds that are parallel to the plane of the ring, while there are also axial bonds that are perpendicular to the plane of the ring. So bonds that are parallel to the plane of the ring are called as equatorial, and bonds that are perpendicular to the plane of the pyranose ring are called as axial bonds. So it is basically energetically favorable for large groups to lie along the equatorial position rather than the axial position, because equatorial bonds point away from the other groups and lead to less steric hindrance. So if you look at the beta D-glucopyranose, you will see that all the large hydroxyl groups point at the equatorial position, and hence there is less steric hindrance in the beta D-glucopyranose as opposed to alpha D-glucopyranose. Now let's just take a hypothetical example of say the cyclohexane structure that you see on the right hand side. So if you look at this structure, you notice the two blue groups, blue circles basically, that are attached to the first and the third carbon of this ring structure. So both these round groups that are depicted in circle point in the axial position. So these groups, because they point in the axial position and they're bulky, what will happen is they will bump into each other as their electron densities will repel each other. So just keeping this in mind, let us just again go back to the structures of alpha D-glucopyranose and beta D-glucopyranose in their chair conformation. And let us just again have a look at the placement of the hydroxyl group in both these chair conformations of glucopyranose. So in alpha D-glucopyranose, out of the 4 hydroxyl groups that you see here, which are placed in equatorial position at C1, 2, 3, and 4, the hydroxyl group at carbon 1 has hydroxyl pointing in the axial position, which is basically a high energy position, which means that there is more steric hindrance in this case. Now, if you look at the placement of the hydroxyl group in beta D-glucopyranose, you see that all the hydroxyl groups, including the one at position carbon 1, are all situated, are all placed in equatorial position, making thereby this avoids steric hindrance within the beta D-glucopyranose structure, and hence the beta anomer of glucose is favored because all the bulky groups or the hydroxyl groups lie along the equatorial side, thereby avoiding steric hindrance. And so at equilibrium, when glucose solution mutarotates, the predominant form that you will find in that aqueous solution of D-glucose would be beta D-glucopyranose because it's a more stable structure. In an aqueous solution, because there is an intramolecular rearrangement that will be taking place within the linear molecule of D-glucose, what you will normally observe is that the cyclic forms will predominate as opposed to the linear form. So more than 99% of the sugar would be existing in cyclic form, while less than 1% exists in the linear form because the cyclic forms are more stable. And amongst the cyclic forms, the beta form will predominate in case of glucose because the beta form is more stable as all the bulky groups lie along the equatorial side, thereby avoiding steric hindrance. And so the answer to the question that why beta anomer of glucose predominates in aqueous solution is simple because you can just simply answer by saying that all the bulky groups in the beta glucopyranose are placed along the equatorial position, because of which there is less steric hindrance, and hence this structure is more stable than its alpha anomeric form. So similar to the hexoses which attain a pyranose form, pentoses can also cyclize and give rise to a 5-membered ring. So for example, ribose is a pentose sugar, fructose is a hexose sugar. And in case of ribose, if there is an intramolecular cyclization, it will lead to the generation of both the alpha and beta forms. But what we have represented here for simplification is just the beta form. The 5-membered ring forms can exist in the envelope form because if you look at the structure, it looks like an envelope. Okay, so if we apply this analogy to the 5-membered furanose ring, we see that 4 of the atoms, if you look at the C2 endo structure of ribose, 4 of the atoms at C1, 2, 4 and the oxygen atom, they all lie in the same plane. The second carbon in the case of C2 endo is puckered, while the third carbon in the case of C3 endo is puckered, and these structures are referred to as the envelope form. So unlike the hexose sugars where cyclization leads to the generation of pyran ring structure, here in case of pentoses, for example, as we have seen in ribose, it leads to the generation of the C2 endo or the C3 endo form, and because it represents these structures look like an envelope. In the case of 6-membered sugar, the pyranose ring exists in the chair form, while in the case of 5-membered sugar, the ring form will occur in the puckered form. So you will see a C2 endo puckered form if the C2 carbon is puckered, or you will get a C3 endo puckered form if the C3 carbon is puckered in case of the pentose sugars like ribose. And we know that ribose is an important constituent of DNA and RNA. And in DNA and RNA, ribose will exist as the 5-membered ring that is shown here. And just like glucose, ribose is also an aldose. So since sugar molecules have aldehyde group or the keto group, the sugars can undergo reactions typical of aldehydes and ketones. So let's just have a look at what are the different reactions that sugars can undergo. So sugars can be oxidized either at their primary aldehyde group, or they can be oxidized at the alcohol group, which is placed at position 6 for D-glucose. So if upon oxidation, the aldehyde group is oxidized, it is converted to carboxyl group. In that case, the molecule that you get from D-glucose is called D-gluconic acid. If it's the primary alcohol group that is present as C6, which is circled here, if that gets oxidized, then you end up getting D-glucuronic acid from D-glucose. Sugars or glucose can also undergo reduction reactions under the presence of mild reducing agents like sodium borohydride that you see here. So D-glucose upon reduction is converted to D-sorbitol, while D-fructose can be converted to two compounds, D-sorbitol and D-mannitol. So sorbitol, mannitol, etc., they are referred to as sugar alcohols, and unlike their parents, which is glucose and fructose in this case, the sugar alcohols are optically inactive, which means that these compounds, unlike their parents, are not able to rotate the plane of polarized light to either right or left. In other words, it means that the asymmetry in these sugar alcohols has been lost, and hence they are rendered optically inactive. So now let's just have a look at a series of reactions that can be used in laboratory conditions to quantitate sugar in an aqueous solution. So some of these reactions are also important because they can distinguish between aldoses and ketoses. One of a very simple reaction that is used to distinguish an aldose from a ketose is makes use of an aqueous solution of bromine. So when an aqueous solution of bromine is added to a solution that contains an aldose, the bromine, which is reddish brown in color, becomes colorless, while the aldose sugar, if it is a glucose, it is converted to aldonic acid. So glucose will be converted to gluconic acid. So you can monitor the disappearance of the reddish brown color in this test. And if the color of the bromine, aqueous solution of bromine, disappears and it becomes colorless, then you know that your tube contained an aldose. There is a second test which is called as the Selivanov's test, which is used to distinguish a ketohexose from an aldohexose. So Selivanov reagent contains resorcinol plus hydrochloric acid. So if your sugar solution has a ketohexose will be dehydrated to form hydroxymethyl furfural. This hydroxymethyl furfural will react with resorcinol in the Selivanov's reagent and will give a red product, as you see in the tube here, within 2 minutes. If it was an aldohexose that was present in the tube, then this red color that was formed within 2 minutes for a ketohexose will be formed much more slowly. And so this is a very, very common test that is used to distinguish between a ketohexose and an aldohexose. Another reaction that is very specific to the presence of a functional aldehyde group can be done by using Tollen's reagent or Benedict's reagent or Fehling solution. So here, what these reagents basically do is that they react with the functional aldehyde group of an aldose to give rise to a carboxyl group, and this conversion of the aldehyde group to the carboxyl group can be monitored because these reagents will change their color. So for example, if you use Tollen's reagent to quantitate the presence of an aldose in a sugar solution, what you end up getting is a precipitate on the sides of the test tube, which looks like a silver mirror in case of Tollen's reagent. In case of Benedict's reagent, the Benedict's reagent to start with has a blue color, but when the aldehyde group is oxidized to the carboxyl group, it is converted to a red solid precipitate. So if the hexose or the aldose sugar here is glucose, the end product that we get here is gluconic acid, and the conversion from glucose to gluconic acid in case of Tollen's reagent is followed or quantitated by the appearance of a silver mirror on the walls of the test tube for Tollen's reagent, and is monitored is monitored by the appearance of a red solid precipitate if we are using Benedict's reagent to test for the presence of aldose. Now, aldehydes are easily oxidized by these mild oxidizing agents such as Tollen's reagent or Fehling's reagent or Benedict's reagent, as I've mentioned here. Ketones do not have such reducing properties and should not ideally be oxidized under similar conditions. So why do aldehydes get oxidized by these reagents? They get oxidized because of the presence of the hydrogen atom in the aldehyde group gives reducing property to the aldehyde molecule. Now, since this hydrogen atom is absent in the ketoses, so ideally ketoses do not have these reducing properties and should not be oxidized by Tollen's reagent or by Benedict's reagent. So therefore, Tollen's reagent, Fehling's reagents, or Benedict reagents can be used to distinguish aldehydes from ketones. However, what happens is fructose is also able to reduce such reagents even though it contains no aldehyde group. And let's just see why that happens. So in spite of the fact that fructose, which is a ketose, does not have the hydrogen atom, it still reacts with, gives a positive test with Tollen's reagent or Fehling solution or Benedict's reagent. That's the question we asked just now. So the answer to that basically lies in the fact that fructose is able to react with these reagents because these reagents are basic solutions. And what happens is fructose under these basic conditions is readily isomerized to a mixture of aldoses. And so as you see here, ketose can equilibrate with isomeric aldoses via the formation of an intermediate that is called as an enediol. So basically what you can say is that Tollen's reagent reacts with aldehydes. Ideally, ketones, because they do not have ketoses, because they do not have the hydrogen atom, should not be reacting with this reagent. But because these reagents are basic in nature, the base in this reagent promotes enediol rearrangement, as we saw previously in the ketoses, leading to the generation of isomeric aldoses. And so ketoses also test positive with Tollen's reagent. So all sugars or all monosaccharides that have a free aldehyde group available are called as reducing sugars, and all these reducing sugars will test positive with Tollen's reagent. So in the case of glucose, as you see here, the Tollen's reagent will convert the functional aldehyde group to a carboxyl group, which is then, the byproduct that you see here is the appearance of a mirror on the walls of the test tube. So glucose is converted to gluconic acid in presence of Tollen's reagent, and the appearance of the silver mirror on the walls of the test tube can be monitored. And when this mirror appears, you can say that the sugar solution that you have been provided with contains a reducing sugar. So because Tollen's reagent is basic in nature, and as I said before, it promotes enediol rearrangement in ketoses, because of that, the ketoses will react positive with Tollen's reagent. And so here you see what happens to fructose when Tollen's reagent is added to a solution that contains fructose. So fructose form will be converted to a 1,2 enediol. You see that the double bond that was at C2 has now moved between carbons 1 and 2, and that is why this enediol is called as 1,2 enediol. And this enediol can then lead to the generation of a mixture of aldoses, and in case of fructose it's glucose and mannose, and because the end product is the generation of these aldoses will then test positive with Tollen's reagent. So basically it's not the ketoses like fructose react positive with Tollen's reagent because the basic nature of this reagent promotes the formation of enediol, and the end product that is generated is a mixture of aldoses. And since we know that aldoses normally will test positive with this reagent, so when you get a positive test, it is basically because of the generation of these aldoses from the ketose that gives a positive test for fructose when Tollen's reagent is added to a solution containing fructose. So previously we have seen that under mild oxidizing conditions, either the aldehyde group will be converted to the carboxyl group, or it would be the primary alcohol group that can be converted to the hydroxyl group. But if you use a strong acid like nitric acid and add it to a solution of glucose, you will see that both the aldehyde as well as the primary alcohol group are converted to carboxyl group, and this gives rise to glucaric acid. So oxidation by nitric acid will convert glucose to glucaric acid. The other test specific for sugars is called Osazone test, which was a test that was discovered by Emil Fischer, which basically makes use of the compound called phenylhydrazine. So excess of phenylhydrazine in presence of acid hydronium is added to a solution that contains an aldose or a ketose sugar, and what you end up getting is a double phenylhydrazine derivative of aldose and ketose, and this double phenylhydrazine derivative is called as Osazone. So why is this test important? This test is important because what happens is that if you add sugar to water and make a solution of it, the solution will get more and more syrupy, but you will never end up getting crystals of sugars from this aqueous solution. Now, as opposed to this, supposing if you take a sodium chloride solution, evaporate it, what you will be left with is sodium chloride crystals sticking to the wall. But if you do a same kind of thing with an aqueous solution of sugar, you will never end up getting sugar crystals. What you will end up getting is more and more syrupy solution, as I mentioned before. So you won't be able to recrystallize sugar like you can do for, say, sodium chloride. So if you make the Osazone, what you are basically doing is you are basically able to now crystallize the sugar, or you're able to obtain the sugar in the crystallized form. So if you take phenylhydrazine and add it to a solution that contains an aldose or a ketose in presence of acid hydronium, what is going to happen is Osazone derivatives will be formed, and these Osazone derivatives will fall out of the solution as a precipitate. So you have to remember two things here. Osazone formation or Osazone test is a way by which you can crystallize sugar. And if you look at the series of steps that lead to the formation of a sugar osazone, you will see that you actually need a free functional aldehyde group for the phenylhydrazine to react with the sugar. So if you remember, we said that if you have an aqueous solution of sugar, the cyclic forms predominate in the aqueous solution, while there will be very little bit of linear form that will exist in the aqueous solution. So what happens is, in an aqueous solution, the phenylhydrazine will react with the linear form, not with the cyclic form, because the linear form is the one that will have the free aldehyde group. As the linear form will react with phenylhydrazine, what will in presence of acid hydronium, what will happen is more and more of cyclic form will get converted to the linear form. So in other words, as the linear form gets depleted of the aqueous solution by reacting with phenylhydrazine, the equilibrium shifts from the cyclic form to the linear form, and so more and more of the cyclic form will be converted to the linear form. So this linear form will then continue to react with phenylhydrazine in the presence of acid hydronium. The acid will protonate the oxygen of the aldehyde group, followed by reacting with the first molecule of phenylhydrazine. Now, since this free aldehyde group is not present in the cyclic form, it is exclusively the linear form that will react with phenylhydrazine to give rise to osazone derivatives of the sugar. So this is point one. You have to remember that osazone test will only be positive for the linear forms of sugar where the functional aldehyde group is still available to react with phenylhydrazine. And in this test, we see that one molecule of phenylhydrazine goes to carbon 1 and the second molecule of phenylhydrazine will go to carbon 2. And for osazone formation, what we're doing is for every one molecule of glucose, we're actually using 3 molecules, 3 times as much as phenylhydrazine to react with the sugar molecule. The byproducts that are generated in this reaction are aniline, ammonia, and water. And so you see that glucose and mannose, both of them will give rise to a common osazone derivative. These osazones, because they are crystals, they fall out of the solution, and depending upon the kind of sugar that we began with for the reaction, the shape of these crystals will differ. So for example, glucose gives broomstick or needle-shaped crystal, while maltose will give sunflower-shaped crystal. And glucose, fructose, mannose, all of them will react the same way with phenylhydrazine and will give the same osazone derivative. So another reaction that is used for shortening the chain length of monosaccharides is called Ruff degradation, wherein an aldose chain can be shortened by oxidizing the aldehyde to carboxyl group followed by decarboxylation. So basically in Ruff degradation, if your starting sugar molecule is a glucose, then what you end up getting is an arabinose, which is a 5-carbon sugar. The reaction involves the removal of the aldehyde group at C1 along with the first carbon and the creation of an aldehyde group on the second carbon. So in the Ruff degradation, the calcium salt of an aldonic acid is oxidized with hydrogen peroxide. So in this case, the aldonic acid is gluconic acid because we've started with glucose, and this gluconic acid is then oxidized with hydrogen peroxide in the presence of ferric ion. Now, where do you get this calcium salt of aldonic acid? So this calcium salt of aldonic acid is necessary for the Ruff degradation and is easily obtained by oxidizing an aldose, in this case which is glucose, with an aqueous solution of bromine and then adding calcium hydroxide to the reaction mixture. So the first step basically involves the generation of the calcium salt of the aldonic acid. This calcium salt of aldonic acid, which is gluconic acid, can then be oxidized with hydrogen peroxide. The ferric ion that is present in the reaction will catalyze the oxidation reaction, which will cleave the bond between carbon 1 and carbon 2, forming carbon dioxide, which is aldehyde group, and generating a sugar molecule which is now been shortened by one carbon. So glucose will give rise to arabinose, which is a pentose. On the similar lines, if you use arabinose as the starting material, which is a pentose, you will end up getting a tetrose. From a tetrose, you can get a triose. And so Ruff degradation is commonly used for shortening the chain length of monosaccharides. So while Ruff degradation is used to shorten the chain length, Keeliani-Fischer synthesis is used to lengthen the aldose chain. And the end product during the synthesis is a mixture of C2 epimers that are generated. So basically, in other words, if you apply Keeliani-Fischer synthesis to a sugar solution, that contains a tetrose, then you will end up getting a pentose. And if you start with pentose, you will end up getting a hexose. So in the first step of the synthesis, the aldose is treated with cyanide and HCl. Addition of cyanide ion to the carbonyl group creates a new asymmetric carbon, and as a consequence, two cyanohydrins are generated that differ only in configuration at carbon 2. The configuration of the other asymmetric carbons do not change because no bond to any of the asymmetric carbon is broken during the course of this reaction. So Keeliani, when they discovered when they went through the synthesis process, they went on to hydrolyze the cyanohydrin to aldonic acid, and Fischer had previously developed a method to convert aldonic acid to aldoses. So this reaction sequence was used for many years, but the method that is currently employed to convert the cyanohydrins to aldoses was modified by Siriani and Barker in 1979, and it is referred to as the modified Keeliani-Fischer synthesis. So in this method, the cyanohydrins that were converted to aldonic acid and then to aldoses are now first converted to imines by using a partially deactivated palladium on barium sulfate catalyst, so that the imines would not be further reduced to amines. Instead, the imines can then be hydrolyzed to give rise to aldoses. And as you can see in this series of reaction steps, you start with an aldose, and because of the addition of the cyanohydrin, one carbon atom has been added to the sugar chain, and then the end product that you have has a carbon that has been has an extra carbon, and so if you start with a pentose, you end up getting a hexose, and if you start with a tetrose, you end up getting a pentose. So Keeliani-Fischer or modified Keeliani-Fischer synthesis can be used to lengthen the chain length of aldoses. So monosaccharides can also undergo certain kind of modifications, and one such modification leads to the generation of deoxy sugars. So if you look at the structure of deoxyribose, you will see that at carbon 2, the hydroxyl group has been replaced by a hydrogen group. And because the hydroxyl group has been replaced by a hydrogen group, the sugar is called as deoxyribose, which is an important component of DNA. L-fucose is another example of a deoxy sugar where the hydroxyl group at position 5 has been removed. L-fucose is found in seaweed and is one of the few L sugars which is a component of polysaccharides. So another modification in monosaccharides leads to the generation of amino sugars. One example of an amino sugar is N-acetylneurominic acid, which is also called as sialic acid. Here, one or more hydroxyl groups have been replaced by an amino group, which is often acetylated. So if you look at the linear structure of N-acetylneurominic acid, you will notice that it is actually derived from N-acetylmanosamine and pyruvic acid. The upper part of the linear structure, which is colored in maroon, is the pyruvic acid component of N-acetylneurominic acid, while the rest of it is the N-acetylmanosamine component. So N-acetylneurominic acid is an important constituent of glycoproteins and glycolipid, and like I said, N-acetylneurominic acid and its derivatives are also called as sialic acid. So these amino sugars are important constituents of glycoprotein and glycolipids, and this tells us that the modifications, how important the modifications in monosaccharides are. We've already seen how two monomers can be bonded or linked to each other by the formation of glycosidic bond. So an alpha D glucose can react with methanol to give rise to methyl alpha D glucoside or methyl beta D glucoside, and then these two molecules can be linked to each other by the formation of a glycosidic bond. So not only glycosidic bonds can form between these two kind of monomers, but N-glycosidic bonds are also important in linking ribose to purines and pyrimidines in nucleic acid, as shown below in this figure. So the N-glycosidic bond here in the figure shown below form between the anomeric carbon and an amine. And these are the bonds that link D-ribose to purine and pyrimidines in nucleic acid. Now, similar to the peptide bonds, the glycosidic bonds hydrolyze extremely slowly under physiological condition in the absence of enzymes. Hence, an anomeric carbon that is involved in the formation of glycosidic bond cannot freely convert between its alpha and beta anomeric forms. Saccharides having an anomeric carbon that hasn't formed glycoside are termed reducing sugars, while saccharides where the anomeric carbon is involved in the formation of the glycosidic bond are termed non-reducing sugars. So with this, we have come to an end of this module, and we have seen how carbohydrates are important and how two monomers are linked through a glycosidic bond in order to build long-chain carbohydrates. So now let's move on and have a look at what all we have learned from this particular module. So with this, we come to the end of the module. So let us just go ahead and summarize what we have learned in this entire module. So sugars are compounds that contain either an aldehyde or a ketone group and two or more hydroxyl group. Basically, these are polyhydroxy alcohols. Monosaccharides contain one or several chiral carbons or asymmetric carbon centers, due to which they can exist as stereoisomers. The structure of sugars can be represented in various ways, such as you can represent sugar as Fisher projections or as Haworth perspective formula. Enantiomerism and diastereoisomerism are different kinds of isomerism that are observed in monosaccharides. Monosaccharides are able to form a cyclic structure due to the formation of hemiacetyl or hemiketyl, which generates the alpha and beta anomeric forms of sugars. Various chemical tests can be used to differentiate between aldoses and ketoses, as we have seen in the module. Two monosaccharides joined together by a glycosidic bond will generate a disaccharide. And so, oligosaccharides are basically short polymers of several monosaccharides joined by glycosidic bond.